Okay. Well, now that we've had our lovely fire drill,
And wasted 15
and we have turned in our topics, and cause what to be launched?
Mountain Dew.
Mountain Dew.
That's going to be returned. You're getting hit in the face with Mountain Dew repeatedly. Not liquid, the bottle.
Yeah, I'll have to get down with some thought later. All right.
To measure the force of which we're going to leave water and the weight, the height of the drops on the bottom.
All right, so what I have here is a resistor. It's stripes stay red, red, black. What is that?
What did you say?
Red, red, black.
Black, red,
black,
yeah.
yeah.
Red, black,
And the stripes, the color stripes.
Oh.
Close. Two tubes. So that would be how much?
That's
2
200.
times 2 to the 0. 2 times, what is it? What does that mean? 2 times,
No, 22.
22 times 10 to the 0.
22 times 10 to 0. Or in other words, how many ohms? 22 ohms. Okay, so that's a fairly small resistor value. Now what I'm going to do is just plug it in directly. And all of you come up here and you can experience this for yourself. Resistors have no sides to them. And one in, so. And turn it on. You say nothing exciting happens. It's true. Unless you touch the resistor.
Wow.
It's
Go ahead.
it's a delayed reaction.
You don't have to. Because
Oh, it's not smoking.
It's smoking. Right. And it's not because it's on pot.
That was funny, I'm sorry.
That was actually.
So the question is, why in the world would it get so hot? I turned it off so it would stop smoking. And no smoking environment after all. So why would the resistor get so hot?
Could you theoretically get high off the heat? Because there's no place for
What's that?
you get high off of the heat.
Why?
No.
Why would you even ask that?
Can I smack him?
You can get cancer off the tube. Is that like getting high?
Close enough.
Oh, man.
You'll eventually get payments.
Oh,
So why is it getting so hot? What's going on?
It's resisting with nowhere to go.
Resisting with nowhere to go.
The current,
Current is too much. Okay.
and there's no where for the current to go after resistance.
All right, you say after resist. What does it mean that the resistor resists current?
I'm gonna,
We need a picture.
the power runs through the wires, goes through the resistors, and the resistor kind of, it doesn't conduct electricity well, so it doesn't travel as well through it, so it goes.
Wait, give me a microscopic picture. I've got little pieces of charge coming through the resistor. How is it that the resistor doesn't conduct very well? What is it doing to not conduct?
There's some form of barrier between the charge, it's the jump, or
Okay.
there's something in the way.
What's the picture that we used?
That's simple, it's just
Perhaps some words around that. That's not an answer. Zigzag. So what's happening? Here comes a piece of charge, and what happens to it?
It gets less.
It doesn't get less, charge is conserved.
Something is less. What is it?
The current.
Current or something. Voltage, I don't
No, not current. Now, the voltage drops,
Yeah, that's what
which means that the energy of that piece of charge. Why am I calling it a piece of charge? What are the real charge carriers in metal? Electrons. But there's a funny thing about electrons. Which way are they going? From where to where? Negative to positive. Whose fault is it that we think Ben Franklin? That's right. So we're going to picture this in terms of a little piece of positive charge going from plus to minus, even though we understand the picture is opposite of the reality. Okay. So you have a little piece of positive charge going from plus to minus in our picture. And so how is it that the resistor resists?
restrict election.
How?
Negative charge.
What
Just
does
because of the
it,
material it is. Material.
what does it force the charge to do?
It goes from negative to positive, and if the resistor is negative, it's forced.
Now, there's not a back EMF on it. Now, motors will do that. You get a motor spin, and as the motor spins up, you get a back EMF that restricts current. Resistors are not like that. Yes. The resistor provides a non-straight path for the electrons to travel. Think bouncing. Think it. Right? And so the key here is that the electrons are now going to be colliding with atoms. And every time the electron collides with an atom, a certain amount of energy is lost to heat. We could. We're not going to. I'd actually have to use a larger parts. Get it to actually explain it. It would be exciting. At one of the robotics competitions a couple of years ago, I saw a robot catch on fire. That was exciting. Did you see that? Were you there for that?
I don't think so.
It was at Mary's Ridge. It was in the cafeteria, and it was the Under the Sun team. And what had happened was that they had screwed in a motor controller, and they had accidentally somehow pierced the plastic container so the metal was touching the frame of the robot. Basically, they were just dumping current directly from their battery through the frame of the robot. And it was flames. It was exciting.
That was last year, right?
Might have been last year. Yeah, might have been last year.
Started a brush
You could use that to most people.
Why? All right. So, what we'd like to do then is to consider the amount of power that's dumped through this resistor that causes it to smoke and potentially catch on fire.
Should we go back to our seats?
Yes.
What you doing now? I'm playing Clash of Clans.
He's looking up Mountain Dew repeatedly hit in the face.
You need to take a video of that. You need to take a video of that. They would crush it. The liquid would come out.
Mr. Curtis,
Yep.
instructional does really cool stuff for fun.
What's that?
Instructional does really cool stuff for fun.
You also have an Apple II watch. You do. It's really funny.
I feel like they
Um, So first of all, what can you tell me about the current that goes through this resistor here? What law will determine that current? Well, indirectly, but more specifically, how do I find the current through the resistor?
V for IR.
What's that called? Hence, resistance is measured in Ohm's law.
We know
So
that
this is Ohm's law that governs the resistor. All right, now, that's it. Now, you want to think in terms of microscopic picture. What we have is little pieces of positive charge. We understand that's a fiction. Little pieces of positive charge come into this resistor and they bounce around. That's a little symbol we've got there for the resistor. Right? They bounce around inside the resistor, and on every bounce, there's going to be a certain amount of energy lost. And so the question is, how much energy is lost? And we can actually compute that, because we know that voltage or potential is related to energy in this way. The amount of energy that is lost is going to be equal to the voltage drop across that resistor times the amount of charge that goes through, because a volt is a joule per coulomb, measuring how much energy per unit charge we have here. And if I want to convert this into power, I just need to convert that into a rate of change by dividing both sides by delta T. So that power, the amount of energy that is lost through a resistor, is equal to voltage times delta Q over delta T. But we have a name for delta Q over delta T, the rate of flow of charge. What do we call that? No.
Velocity.
That's for an individual electron. We're talking about aggregate. What do you call it when you stand at a point and you can't count how many electrons come through per second? Somebody said it. That's current.
yeah.
Yeah. And so we arrive at our first and primary equation to compute the amount of power that is dissipated by a resistor, or actually by any electrical component. And that is power equals, here's the way the electricians say it, volts times amps. Power equals voltage times current. Well, all right. Okay, so this makes a little bit of sense here. In my other class, I discovered something kind of wild. Nobody uses hair dryers anymore. Okay. So let's see here. What appliances do we actually use?
Microwave.
Microwaves. How many watts is a microwave oven?
6. And, microwave oven. 1200.
1200 watts. That works for me. So, for example, we have a 1200 watts microwave. And what we'd like to do now is to understand a little bit more about where this power is coming from. Well, the microwave plugs into a wall outlet, and what everybody needs to know is that in the United States, wall outlets are 120 volts average.
Is that like plus or minus 1 or something?
Well, no, it's really 117, but the reason I say it's average is that it's an AC current. It's in the form of a sine wave,
Yeah.
with an amplitude and blah, blah, blah. So to take that sine wave and you average it over, you average its power, then it averages out to 120 volts. So that's, yes indeed. So if you go to Europe, many European countries are going to have 220 volts as their standard outlet. In Korea, what is the wall outlet? 220. So little kids have to be really careful, right? Touch it. Need metal
That is so
really.
Well, I mean, in Korea you use metal chopsticks, so there are some like
electric
semantics.
Oh, look at it. No, I just didn't know that metal chopsticks were a thing. I thought they were all made.
You've got to wash them. Just gonna throw them out after every time.
Okay, so if we asked then how much current is flowing through this microwave on average, we would say power is equal to volts times amps. And the point of this equation is that you should be able to do a lot of these calculations in your head without even reaching for the calculator. How many amps are we drawing through that microwave oven? You can do the same kind of computation for a light bulb. Everybody find the amount of current going through a 100-watt light bulb. Now illegal to be sold in the United States. They search.
Wait, it is?
Yeah.
incandescent bulbs,
It's illegal to own them.
No.
Okay.
you just have to have some.
Some massive
Yeah.
stuff.
You can show your children. And this children's secret steps. In a more enlightened time.
This is your inheritance, my
Go tungsten, young man.
Light bulbs.
That's right. Silk Road. Get your opium here, get your light bulbs. The other Home Depot. Oh, boy. All right, tell me how the calculation goes.
Sorry.
Underwater light bulb, what is its current draw?
Underwater 100 equals
0.83 or 2%. Okay, there you go.
Yeah, 1/12, so.
No, it's 10 over 12.
Oh, yeah, 10/12. Yeah. Wrong number.
No. You know it has to be close to 1.
Yeah.
Yeah. Okay. Well, let's actually go a little further with this because we just by knowing this, we could actually figure out the resistance of that light bulb also, which is kind of cool.
We have the V.
Yes.
I, now we get back to the R.
So since V is equal to IR, and we know it's 120 volts, and we know the current is 0.83 amps, and the R is how much? Yeah, this one, I think we're reaching for the calculators, unless you want to compute 720 over 5 by
144.87.
exactly 144 ohms if you carry it out infinitely, just like that. So there you go. Now you know the resistance of a 100-watt light bulb. Ta-da! But it's interesting because you would, what other elements, what other appliances besides light bulbs basically have a big resistor whose job is to produce heat? Ovens.
Hair dryer.
Hair dryers. Curling irons.
Anything that gets really hot in a small area.
It gets really hot in small areas. Water heaters, the water heater elements. If you ever have the opportunity to change the water heater element, it's actually kind of a simple job. But you have to make sure you turn off the power to the water heater first.
So they have some heaters that
Whenever you're
like a small room heater.
Yeah, room heaters of any sort. Baseboard heating. Now your heat pump is a little more sophisticated than that.
That's right, so like the single room heaters.
Okay. So there's that. What I'd like to do is, we ended up finding the resistance of this guy in 2 stages. I'd like to take our equation and make it a 1-stage equation. So our primary equation is power equals volts times amps, right? But if I also know that V equals IR, then I can substitute, and I get a second equation for power, which leaves voltage out of it, I squared R. And this equation is interesting because it tells us that if I'm trying to pump a fixed amount of current through a circuit, then I want the resistance to be as low as possible if I don't want to waste a lot of heat. So, for example, power companies want their transmission lines to have as low a resistance as possible, and they also want to pump as little current as possible through them. So the way that they'll do that is on the transmission lines, they use a really high voltage and a small amount of current, and then transform that to a much lower voltage and much higher current down to the user range. And that way they have very little, what they call I squared R losses through the power lines. The second thing that I can do to get our third equation is to recognize that not only is V equal to IR, but also I is equal to V over R, right? so that I can replace I with V over R and get a third equation that's very, very interesting. Power is also equal to V squared over R. Meaning what? Meaning that if I'm trying to have a fixed voltage drop, the easiest way to do that without losing much power is to have a very high resistance. Because if I have a low resistance, then I have to pump a lot of current to maintain that fixed voltage drop.
So if you have no resistance, it's impossible.
If you have no resistance, it is impossible. Which means that if you have a short circuit, you're going to have a huge current flow. And your battery's voltage is going to drop to nothing. And if that sounds similar to a robotics problem, then that's not an accident.
I feel like there's a story there.
Yeah.
Is that why robots are so shocking and keep like touching them to make it?
Actually, your problem was what we'll do tomorrow, which is internal resistance.
So it's like so statically like I would have to like touch it every match and like get all of it out and it's shocking.
Yeah, that actually was happening simply because as the robot was rolling around on the rubber mat, it was picking up little bits of charge. Every time the wheels would go by, they would pick up little pieces of plastic, essentially, and extra charge. And that frame is a really good conductor of charge, but because it's on the wheels, it's not going to conduct it out to the mat.
So it only sucks it out.
Yeah, I actually saw one robot that was dragging a chain, trying to dissipate some. She's dragging a piece of copper wire or something, trying to dissipate charge. It was an entanglement hazard was the problem. And so if you touch the frame, now all of a sudden the charge from all over the robot goes zoop, right to you.
Yes.
And you get electrostatic discharge. Which is, for you, it's kind of annoying, right? And then you touch it and you're like, oh yeah, that's right. It's like a cat. But if you actually look at circuit components that have had electrostatic discharge, it's like they were hit with a huge meteor. At the atomic level, basically the electrostatic discharge vaporizes atoms because it gives them all the same charge in a really small spot, right? And they just, they scatter.
This is a bit of a tangent, but when I was lying in bed over the weekend and I had my headphones in and my sheets were really just came out of the dryer and were really charged, and I kept getting shocked in my ears. All the static from the
That's actually the music you were listening to.
Oh dear God, I hope not. It's classical.
We call it static metal.
I thought you called it electric, or electronic music.
It makes me want to bang my head!
Yes, I listen to classical music. What's so weird about this bed?
That's weird.
Yes, it is.
I thought I was weird.
No. Yeah, no.
Yeah, no, I listen to classical. As well as other stuff.
What do you listen to?
Kind of a stormy sport. Okay. I want to compare and contrast a couple of things. We're going to take a 50 ohm resistor and a 5 ohm resistor, and we're going to put them both in a circuit. First in series, and then we'll come back and do it again in parallel. Parallel is easy. Maybe let's do parallel first. Anyway, we will do parallel first because you can do this one in your head. First question, how much current is flowing through each resistor? Second question, how much power is is being dissipated through each resistor? So in your head, no big one. Now you're working too hard.
No, that's technically the equation.
Yep, you're working too hard. What is the voltage drop across each resistor? 10 volts. Yeah. So how much current is going through the 5 ohm? 2 amps. That's right. And how much current is going through the 50 ohm? 0.2. Okay. Next question. How much power is being dissipated by each one? Which of the equations do I want? Do I want power equals volts times amps? or power is equal to I squared R,
I squared.
or power is equal to V squared over R.
I squared.
I squared R? Okay. You do it that way, I'm gonna do volts times amps. If you do volts times amps, what is the power dissipated through the 5? 20 watts. That's a lot for a resistor to handle. The resistor that I had smoking over here is a half-watt resistor. If you exceed half a watt through it, it starts to let you know that it's not happy. All right, and if we do power equals volts times amps here,
2 times 2 times R.
yeah. No, I get 10 times 0.2 is,
No, I was talking about. I thought you said do I squared R for the loss. I said 2 times 2 times
but it's not 2 times 2 times 5.
The one you already
0.2
did.
times
5. I thought you were doing normal ones.
Yeah, 0.2 times 50. Yeah, it's gonna be 2 watts. Volts times amps. Now, what's the moral of the story? Notice that we have, in parallel, a much larger power being dissipated through the smaller resistor. And it's all at a constant voltage. This is how you want your house set up, how you want your house wired. You want all the circuits in parallel, so that when you hit the switch, you're guaranteed 120 volts across each individual volt. All right? Let's see how you don't want it to be set up. It's very in series. Let's see why. We're going to take our same 5 watt, 5 ohm, and our same 50 ohm resistor, and a 10 volt power supply. And now I want you to calculate the current through the circuit and the amount of power that is dissipated through each resistor. Got it. What do you get for the current? 2.2 amps?
And divided by 55.
That should be 10 divided by 55. So that should be 10 volts here, and the equivalent resistance is 55 because they're in series. 0.18, yeah. So the first thing that we notice is that the current is less than the current through either of these, which is expected, right? Because since they are in series, the resistance will be greater than either one individually. Okay? Now, how much power is dissipated through each one? Here, I think we really do need I squared R, because the voltage drop is not 10 volts across each. Go ahead and calculate power drop.
If you're calculating the power, you do that at each one, or do you do it still in this 55?
You're going to do each one separately. You could also do the 55 total. That'll give you the total power dissipated through both.
Okay.
And yes, the power does add.
So
0.162 watts here. And 1.62 watts here. So we notice here that each of these is going to dissipate power proportional to the resistance. In other words, the larger resistor sucks down the larger amount of power of the two. So parallel and series circuits in some ways behave opposite from one another. And that's the bell.